Welcome back to Nature of Code in Rust and GGEZ. In this video, we're going to be going over exercise 2.1. Using forces, simulate a helium-filled balloon floating upward and bouncing off the top of a window. Can you add a wind force that changes over time, perhaps according to Perlin noise? I think that we can. So let's head on over to our code. We are in exercise 2.1. If we run it, it should be what we had last time, which is all of the balls moving towards the mouse. I think that's a fine starting point. So to begin with, let's go ahead and look up our main library and sort of like see what we're doing here. Right, we've converted everything to be in a vector of movers. Well, I don't really think we need to do that anymore. Or at the most, we're gonna only have one. But I think I'm gonna actually just put this back to mover is a mover. We're not gonna create a whole bunch of them. We don't need mover like that. Or we're just gonna create a single one. So let mover equals mover new. We do need to say where we're going to put this. We can put it in the top of the screen. However, with a balloon floating upwards, now let's create into the top of the screen. So we're gonna, sorry, in the middle of the window. So we're gonna have our width divided by 2, our height divided by 2, and we'll store our mover. All right, that's happy there. We don't need to do an entire loop. We don't even need to do this for each. We're just going to have our mover, a self in front of it, and have it walk, update, and check edges. So this walk might be a little bit interesting. What are you upset about? Oh, we have to handle this result. So here, question mark. Oh, and I noticed that this is returning a new does return a game result. Oh no, that should be fine. What are you upset about? Oh, you need a context. That's what you're upset about. There we go. Have a context, be happy. Okay, so we're gonna walk. This is probably gonna be where we're gonna have it to fly or like set up the forces. Maybe we should change this to be something like run. That feels like maybe a little bit more appropriate to us. Like run the mover, like simulate, do the things. We're not gonna have our for loop there. And here we're just gonna update you to be a self.mover display. And we're pretty much back to where we were, except we need to make sure we're handling this run properly instead of the walk. All right, so I'm gonna let's go to our mover and update the walk function to be run. And now it should be exactly the same as what we had before. If we run this, we're going to get a circle that then is constantly moving towards the mouse. Okay, excellent. And it's starting in the center of the screen. So the next thing we want is some kind of constant upward force. And what we notice in the book for this chapter is there's now going to be an apply force that applies, it applies whatever forces we need to acceleration. So let's actually create that here. So pub function apply force. This is going to take a mutable self and some kind of force, which is going to be a point. It's actually a vector 2, sorry. And we don't need to return anything. So what's going to happen in this force is we're just going to add this to acceleration. So self.acceleration plus equals to this force. All right, easy enough. We don't necessarily need a run here. We might even be able to just get rid of this, but the general idea here is that we want some kind of upward force constantly hitting our balloon. So I'm gonna take away this. All of the example code was showing everything happening just here in this update. So I think we can do that here too. So we want an upward force. We can actually create that and just sort of store it globally up here instead of having to recreate this over time. This is kind of like a reverse gravity. It's going to be whatever like our upward force is. So we can, let's see. I'm trying to also think of, should this actually be something that the balloon has and knows about, but I'm not necessarily sure it has. So let's do call it like an up force. This is going to be a vector. Vector 2. There it is. And we can create this and store it away. So that up force vector 2 new. So there's no x movement. We're just going to have a y movement. It's going to be negative something. So we can try negative 0.05. Sort of see how that ends up feeling. We then want to, in update, before we run update, do a self.mover.apply force and pass it in self.up force. Okay, that's happy now. We can, let's see, so apply force is happens, update. All right, so we should now see our balloon rise up. And there it goes. Now it does, we're having the check edges thing, so we probably want to turn that off because we don't really need that. In this case, we want to, when it hits the ceiling, to bounce off the top. And I guess in a way that is check edges, isn't it? But I think I want to create a new one. So let's head back over to here and maybe like similar to check edges. We're going to have a pub function like hit ceiling. Maybe like check ceiling. We don't need a context because we know in this case the ceiling is the top of the screen. That's going to be 0. And the only reason we needed context before was to get the screen width and the screen height to replace it. Okay, so I'm just going to reuse check edges. I'm just going to take all this code and delete it. We have it in the Git history, so if we really need to go back to it really quickly, we can. We're just going to use check edges again. I think it's going to be a little bit simpler and keep, instead of adding more functions to this, which will be nice not to overbloat this this struct if necessary. Okay, so for check edges, if we hit, I want to apply another force downwards that's going to have it bounce down. So the first question is going to be, are we hitting? So the location is going to be the top. So I actually probably want to have a size stored away here. And I don't think we have a size. So let's do a radius. It's going to be an F32. Right now, our radius is just hard-coded here with a 25. Let's actually set that. You can become our radius, and we'll store radius down here. And what this means is we can check to see if the top edge is past the top part of the screen. So if self.location.y, if that minus self.radius, if that's less than 0.0, then we've gone past the top of the screen. So what needs to happen? Well, first of all, we need to reset ourselves to be at at the right location. So self.location.y is equal to 0 plus whatever our radius is. So it's just self.radius then. Okay, that's the first thing. And if we run this, we do have to remember to put check edges back again. We're taking in context, but we really don't need to. Let's go ahead and remove the requirement for context here. It just sort of stops there, and that's fine. Let's go ahead and let's give it like the exact momentum, like whatever we're going up. So our velocity going upwards, let's just have it bounce off by the same amount. So that means when we reset ourselves, we also want to apply a force of the opposite y-wise. So we want to create a new force. So this is going to be called our bounce force. This is going to be we need to clone our velocity. So self dot velocity. I then want to, let's see. I then want to reverse the y on this. So let's make this mutable. So take our bounce force dot y and multiply that by -1. And then let's apply this bounce force to our force. So self dot apply force, bounce force. And let's see, what are you upset about? Variable doesn't need to be mutable. I guess not. Oh, times equals. Now, okay, there it is. That was that warning. The warnings are helpful because it lets us know that something is going wrong. All right, so let's just try this. See if we bounce downwards. Now I'm expecting that we're going to bounce down by far too much. Like, yeah, we can see it's a really far downward bounce, like farther than the screen. We really want to cut. We want to like cut our momentum going down by a significant amount. So once we've made this a negative, let's also bounce force dot multiply scalar. Let's like cut it in half at most. So if we run this again, that's still a really strong force. Let's try to make it like really small, like 0.2. There it goes. Okay, it's not going past the ground. That's still really like a high force. Now this acceleration, oh, you know what? There's something else that we're not doing, I don't think. In our update, we're updating acceleration here. What we really need to do at the very end of all of this is reset acceleration to 0. So we're just going to multiply it by 0, which should help with this. Let's try this again. There we go. This feels a lot better. And this multiplying by 0.2 is way too small. So if we make this back by like 0.5, this should be a little bit more realistic now. No, it's not. It doesn't even have enough to enough power to sort of like bounce off. What if I just don't do that? We take whatever our velocity going upwards is. Is that enough to counter? No, it isn't. It's not enough to counter the downward force. So now we could like multiply it by a significant amount. I'm thinking we probably want to Let's have our up force be a little bit less strong. See how this ends up feeling. It's really slow. Now, if it's not going up that far, I'm thinking there might be a miscalculation with our velocity and like what we think that it is. And is it applying this sort of back downwards force again? So we apply the force self.utForce. When we apply the force, it's just adding that to acceleration. In update, we're taking the acceleration, adding to the velocity, limiting our velocity, which that could potentially be a problem too. We have our velocity then adds to location, and then we reset acceleration for the next frame. Okay, that seems to be fine so far. Check edges is happening after update. I don't think that's too big of a problem because we should have a downward force sort of set up for us here. So I'm kind of curious onto what this bounce force really is. And do I really want to be doing this like Y? I kind of want to make sure that it's a positive Y. And I wonder if that's a problem. I also want to make sure that I am actually copying this. Like if I no, because dereference you. Yeah, it's not right because I was auto dereferencing when I come into self. So that should be giving me a copy of vector of the velocity. So bounce force Y. Let's do a debug here. Debug of our bounce force. Now we're going to get a whole bunch of numbers out because it's going to be going every single frame. Actually, it's going to be going every time it hits this top. So I'll be interested in see what it. All right, so now it's just sitting here. Okay. So our bounce force is just this tiny, tiny, tiny number, 0.005. Now our up force, that happens to be exactly what this is. What is our limit? Our top speed is 10. Okay, that's we're significantly slower than what our top speed can be. So let's like bring this back down 0.5. Our velocity isn't resetting, right? Velocity there. A new one there. Okay, so plus equals to acceleration. Velocity, we limit it to self.top speed. We add location to velocity. Okay, that should be fine. Now we get velocity, we mine it. Okay, yeah, that should be fine there. Let's run this again with a higher. It says 0.5, but the up force is exactly even to what this is. And that's clearly a problem. We want to make sure that velocity is never being reset, which it doesn't seem like it is. Update is keeping velocity where it is. We're not scaling velocity ever. We're just doing our check edges. I mean, we can explicitly clone velocity. It gives us a warning because it thinks that it's an unnecessary clone, but I don't think that's our problem. Because I think it actually is unique. Yeah, it definitely is. Otherwise, that would have been a problem. So our bounce force, do this, figure out a bounce force. Now we can normalize this bounce force, and then we can scale it up. I kind of feel like I want our I don't want our velocity to like just never increase. So inner update. I'm really curious of what our velocity is here. So I'm going to debug self.velocity, and I also wanted to debug it here too, just in case my limitation is actually what's causing problems. So let's try this and sort of see what we've got. So it's just this 0.5. Okay, here we go. It is negative. Okay, it's negative 10.5, negative 10, negative 10.5, negative 10. So it's set to like the negative 10s. And then we check our edges. We hit the top. So our location is above this. We have our bounce force. And apply force is definitely to acceleration. That's good. So that's what we want. We're not doing anything weird here with our velocity, right? Just apply force, update, and check edges. That's appropriate. Okay, so we need to do this. I'm going to go ahead and pause the video. I'm going to tinker around a little bit, see where my sort of logic area is, and I'll be right back. All right, I'm back. I think I figured out what the problem is, and it's not really a coding problem, but rather it's a problem with my just sort of like the math and the physics simulation. So as the balloon moves upwards and it hits the surface, if I just try to apply whatever the current velocity is downwards on it, then I'm going to end up getting a it's going to just sort of freeze eventually, because we're getting the same velocity going upwards, pushing the same velocity going downwards, and that's going to, well, it just neutralizes itself. So it doesn't move at all. And we can see this when we run this, and it just freezes on the ceiling like that. So normally what happens is it goes upwards, it hits, and then the force, like it pushes, the balloon is having a force pushed up against itself. It also has a force that pushes against the wall, or the ceiling in this case. Because the ceiling has such a high mass, when it pushes against it, it actually pushes itself backwards. So it's kind of like doubling its own force. So if I were to take our bounce force and multiply it by 2, so bounce force multiply scalar, so we just scale it up by 2.0, then when we run this, we'll see that, okay, it bounces. I believe it's very slowly stopping, but it's kind of hard to see there. We could potentially play around with changing our top speed around, possibly changing how fast our up force is. Like maybe we can make this 0.3, like a little bit slower, maybe a little bit higher. I'm not sure exactly what the best way to sort of make it look as it is. What we can do is, however, change the force that's hitting against it. So let's make this back to 0.5 here. In our mover, if I say that your force backwards is not quite double, but maybe there's some friction, maybe there's something else, maybe it's like a 1.75. Then we'll see that this comes up to the ceiling, it hits it, it bounces back, not quite as fast as it went up, and then backward up again. And that would be our balloon just moving straight upwards. Okay, perfect. Now, the second part of this is, can we add a wind force that changes over time, perhaps according to Perlin noise? And absolutely we can. So if we want to add a wind force, we can do that up here in our main library. We're going to want to store noise. So we have noise, which is going to be Perlin. We also know we're going to have an X off and a Y off, which is an F64 and an F64 for the Y off. And then we're going to have an incrementer too. Increment by, you're going to be an F64 as well. Start you with like 0.0. You can also be 0.0. I guess in this case, if we're doing X and Y as the same spot, we can just be maybe like just the first one. You can just have an X off. And then we'll have noise meant by your, let's do 0.01. All right, what are you upset about? You need a equals, not a colon. Okay, everything's happy here. All right, then down here in update. So if we want a wind force, we can generate that here. So we can do a wind force. Let's make this mutable also. Equals, this is going to be self.noise get. We're going to pass it in self.xoff, xoff. That should, let's see. Oh, we have to pull in the trait. Import u. That gives us this F64. I suppose we do need a y off, don't we? Because we want this Perlin noise for the X and a Y, because wind can also push upwards and downwards, not just left and right. So let's also add that here. And let's make this like 10,000. Okay, so this will be wind force X. So we can actually put this inside of a vector. So let's do that here. So vector 2. For the X, it's going to be self.noise.get, and we'll have self.xoff, self.xoff. Then for the Y, self.noise.get, self.yoff, yoff. All right, that gives us a vector 2. Now this is a number between -1 and 1, which should be fine. It's a little bit hard to tell like how good this is going to be. So I'm actually going to just leave this as it is, and we're going to apply it as a force immediately. So self.mover, apply force, and this is going to be our wind force. Down at the bottom, let's make sure to increment our self.xoff. Equals self.noise increment by. And oh, each of these needs to be converted into an F32. Okay, so that adds a wind force. Let's go ahead and see what this feels like. It's hard to tell whether or not it's going to be easy to see. Oh, there it goes. It's definitely moving left and right. And we can sort of like see that accumulative wind power just sort of like eventually just blowing it off the screen. We could handle the edges, not allow it to blow off the screen. So in our check edges, we can also have a self location dot this is x. So if the left hand side, so x dot minus self dot radius, you're less than 0.0, then we need you to basically reset our location. Self dot location dot x is going to be equal to self dot radius. And let's also kill our leftward momentum, our leftward velocity. So self dot velocity dot x is equal to 0.0. Now, else if we now kind of need that context coming in. So context here, we need that so we can get the width of the entire arena. So let's see, width, screen width, and screen height is equal graphics, drawable size, pass in the context. Okay, so if self.location.x plus our self.radius, if you're greater than the screen width, then reset our location, self.location.x. We're going to set you equal to the screen width minus self.radius. And then we're also going to do the same thing where we kill our horizontal velocity. Now this does mean we need to fix this check edges. We need to pass in the context. Okay, let's try this again. And now we should see the balloon can go into the corner of the screen, but it will just sort of stay there and it'll be easier to blow back once the wind sort of comes backwards. It's not going to have like a potentially infinite amount of wind, hanging down. And if I want to make it look a little bit more like a balloon, we can add a vertical line down as like sort of like the string, but I don't necessarily think that's helpful. Oh, and we have that sort of wind that's blowing downwards every once in a while. But I think this is good. Let's go ahead and get rid of some of these warnings. So we're not using RNG. It's true. This time using noise. So we're not using U. Using U. Using U. And there we go. No more errors, no more problems. We have a balloon floating up. So that is exercise 2.1, which is using forces to simulate a helium-filled balloon. Thank you very much, and I'll see you in the next video. Bye.